In this video, we'll look at some example of results we can get using unsupervised pre-training. So we saw the procedure for unsupervised pre-training. What we first do is that we initialize each layer from the first hidden layer to the last hidden layer by training a what we call a greedy module, so either an RBM or an autoencoder on a data set that was generated by transforming the input data into the representation of the previous hidden layer. And then we use the weights and the biases found for that hidden layer that was trained using an RBM or an autoencoder as the initial value for the parameters of that hidden layer in our deep neural network that we want to use for classification. And then we initialize randomly the last part of the neural network, the output layer, and then we train it using regular backprop, which is referred to as fine-tuning. So what we'll see is a few results on training deep neural networks on different image classification problems. So these were generated by myself and my colleagues to get an idea of the performance of deep neural networks in different settings with different pre-training algorithms and different configurations or architectures of the neural networks and so on. So we had a bunch of variations on the MNIST data set where we added rotation. So we see here characters with different amounts of rotation. The incorporation of a random background or background extracted from an actual image taken from the web, and a combination of rotation and some background. Also had another classification problem, visual classification problem, where we have a rectangle in some image and we have to say whether it's taller or wider. For instance, this would be a wide rectangle and this would be a tall rectangle. So these would be two different classes, and this would be a binary classification problem. And then a harder version of that problem where the rectangle corresponds not to a set of black and white pixels, but instead of different, so there's a background and then there's a patch corresponding to the rectangle in question, which was extracted from a different image. And then we have another binary classification problem. We have to say whether the shape in the image is convex. So for instance, in this case, this is not convex because I can draw a line between, say, that white pixel and that white pixel here, and this line goes over black pixels, so it doesn't stay in the white shape in the image. And whereas this would be a convex shape, so these would be the two classes for this classification problem. And so we trained deep neural networks on these different data sets and looked at the result and see what kind of conclusions we could make out of them. Okay, in this first experiment, we'll look at the impact of initialization. So we considered a deep neural network without pre-training, another one with pre-training using a regular autoencoder, or pre-training using the RBM. And in each case, we considered a depth, so number of hidden layers of 1, 2, 3, and 4. So I guess this would be, 1 wouldn't be very deep, but of course 2, 3, and 4 would be considered deep neural network. And then we performed an experiment on MNIST, the original MNIST, but which we refer to as small. So we just essentially reduced the size of the training set, but it's essentially original MNIST digits as extracted from the original data set. And we compared with, and also did experiment with the rotation variation that we generated. So there are three different conclusions we can draw from these experiments. The first thing is that deep neural network actually helps. So in all cases, the performance without, it actually pre-training helps. That's the first conclusion. So if we don't use any pre-training for MNIST small, we get about 4% performance. If we use autoencoder pre-training, we're more at 3.3% error. And then with RBM, you get even better at 2.7. And then a similar conclusion for, say, the rotation, where we get better and better performance in general if we use pre-training, either autoencoder and RBM. The other conclusion we can draw is that pre-training also helps training with success deeper networks. Indeed, the deepest neural network, or I guess the shallowest neural network with performance that's as good as the best performance we can get, in this case, would be 4%. So this is statistically undistinguishable from these two results if with 2 or 3 hidden layers. In this case, however, training 2 hidden layers is better than just 1. And similarly here for MNIST small using either autoencoder and RBM pre-training. So we see that we've been able to train with success a neural network that had 1 more hidden layer using the unsupervised pre-training procedure. And we actually get the same conclusion on MNIST rotation, where the best we could do is 2 hidden layers here and then 3 with pre-training either with autoencoder or an RBM. And then the third conclusion is that by going from a somewhat simple problem, the original MNIST problem, to a harder problem, which is to classify rotated digits, the best performance we obtained was actually with a deeper neural network for the MNIST rotation problem than for the original MNIST problem. So indeed, we went from 1 hidden layer to 2 hidden layer as our best result, from 2 hidden layer to 3 hidden layer as our best result here, and 2 to 3 also with the RBM pre-training. So this sort of confirms our intuition that for more complicated problems, we should have more success and get a better result using a deeper neural network. When we went from MNIST small to MNIST rotation, using 1 more hidden layer actually helped. Okay, so this sort of justifies even more the use of deep neural networks. In these experiments from another paper by these guys here, they did experiment with 1, 2, or 3 hidden layers with either RBM pre-training or in this case they use denoising, autoencoder pre-training, or no pre-training at all. So the no pre-training would be the black line. And what they did is that they varied the number of hidden units in the neural network and saw with just 1 or 2 or 3 hidden layers what was the progression of the performance on so the test set performance in terms of generalization. And what we see is that if the neural network has little capacity, so few hidden units, then pre-training doesn't help. So we get better test error without pre-training than with pre-training. But as we increase the capacity, eventually these two set of lines cross, and now without pre-training overfits. So it has a worse test error than with pre-training. And we get the same shape either with 2 hidden layers or 3 hidden layers. So that confirms that really we're getting pre-training acts as a regularizer, because if the neural network, deep or not, has few parameters, so little capacity, then much like any regularization, what we expect to see is underfitting, so worse result in terms of test error. But as we increase the capacity, then the better regularized model starts doing better. And in this case, the better regularized model corresponds to the neural networks with pre-training here and here. Okay, so again, this confirms our intuition that we can think of pre-training, unsupervised pre-training, as a regularizer. It will overfit less with large capacity, but it will lead to underfitting with small capacity. This other experiment is one where we tried to see what was the best architecture to use in a deep neural network with 3 hidden layers. So if we have 3 hidden layers, we have to choose a number of hidden units in each hidden layer. That can be a bit cumbersome and annoying to do. So here we considered 3 types of choices. One where we would, as we go deeper, decrease the number of hidden units, so decrease the width of the hidden layers. So decreasing width would be a hidden layer kind of like this maybe. And constant would be the same number of hidden units each hidden layer, and then increasing would be more and more hidden units as we get closer to the output layer. Okay, so this is what these 3 set of 3 lines mean here. And then we considered the performance for different total number of hidden units in the neural networks. And here we have the performance either on MNIST small or on MNIST rotation. And here we have performance for each column either with RBM pre-training or autoencoder pre-training. And the general trend seems to be that using the same number of hidden units, so constant width, tends to do either at least as well or better than other options. So normally we see that often the confidence intervals between the different performances overlap with the constant width, and or it's actually doing better, say for instance in this case. So this kind of reassuring. It means that perhaps we can just at least in our first experiments, concentrate on neural networks with the same number of hidden units and just try different number of hidden units for each hidden layer. And here we have the performance on all of the data sets I mentioned before, so not just MNIST rotation and MNIST small, for either SVM, so I'm not going to describe what it is, but it's a very popular type of classifier in machine learning, and here we're using the kernel variant with an RBF kernel. And here we have the results with pre-training with stacked autoencoders, RBMs, or denosing autoencoders, and we always use 3 hidden layers. So first thing we see is that deep neural networks, either the what I call DBN here is really just a stack of RBMs for pre-training, or stacking denosing autoencoders tend to do better than using an SVM, which correspond to a very good but shallow classifier, and so not a deep classifier. We see also that autoencoders tend to perform less well than either RBMs or denosing autoencoders. And RBMs and denosing autoencoders tend to do about as well. So sometimes the pre-training with RBM works better than denosing, and sometimes it's the other way around. And so in practice, in these, we do observe that they tend to be somewhat equivalent in terms of the performance. But on various data sets, it might be that one will work better than the other. So, so they're both really good, reasonable options for pre-training, whereas regular autoencoders might not is not worthwhile compared, say, to just denosing autoencoders. So this confirms what we discussed before, that denosing autoencoders are really a way of improving on the regular autoencoder. All right, so that ends our examples. So we see that unsupervised pre-training is helpful. It helps in terms of regularizing the model, and it also allows us for more complicated tasks to get better performance with deeper neural networks.